Hello everyone, today we are going to look at a very cool part of math, real life uses of convergent and divergent series. I will present the introduction for our group project. I will cover the background, why this topic matters, and our project goals. First, what is an infinite series? Simply speaking, it means adding numbers together forever. To understand this endless adding, mathematicians use partial sums. This means we stop and add just the first few numbers. Then look at how the total changes as we add more and more items. So this brings us to two main ideas, convergence and divergence. If the total sum safely stops at one final fixed numbers, we call it convergence. But if the total never stops and just grows to infinity, then we call it divergent. We use special tools like the ratio test and harmonic series divergence to check this. So many students think that the infinite series are just boring formulas on a whiteboard, but they are actually very powerful tools. We use them every day to solve real problems in finance, medicine, engineering, and computer science. So in the real world, convergence theories help us calculate safe, steady limits like steady blood levels for medicine. On the other hand, divergence theories help us find physical limits. For example, in building structures, they tell us if a repeating system will stay balanced or eventually break down. So our project has three main goals. First, to explain the basic rules of series. Second, to show clear step-by-step math answers for real problems. Third, to use clear charts to show how the totals change over time. Now, let's move on to the next part of our presentation. Thank you.
Okay, thank you, Paul. Now I will continue by introducing the mathematical theory of infinite series. Before we learning how to solve infinite series, we first need to understand what it actually means. An infinite series is the sum of an unlimited number of terms. Instead the stopping after a few number, the pattern continues forever. To study an infinite series, mathematicians do not look at all the terms at once. Instead, then add the terms little by little. This is called a partial sum. By observing how this partial sum change as more terms are added, we can decide whether the series approach a fixed value or keep growing without a limit. This idea is the foundation of all the convergence tests that we will learn later. There are two possible behavior of an infinite series, convergence and divergence. A series converges when the total value get closer and closer to one fixed number, even though more terms are continually added. On the other hand, a series divergence when the total value does not settle at a single number. It may continue increasing, decreasing, or keep changing without approaching a limit. Therefore, the main goals when studying infinite series is to determine whether a series converges or diverges. Now, let us look at several important formulas introduced in this chapter. This formula provides the basic mathematical language for working with infinite series. Some formula describe how an infinite series is written, while others help us analyze the behavior of the series or identify special type of series. It is important to understand when each formula should be used rather than simply memorizing it. Once we once we understand this formula, we can apply different methods to determine whether a series converges or diverges. Before moving on to the example, let us briefly introduce the convergence test covered in this chapter. Since different infinite series have different patterns, there is not single method that work for every question. For the reason, mathematicians have developed several convergence tests, and each test is suitable for a particular type of series. For example, some tests are used for positive series, some are better for series involving power or factorial, while others designed for alternative positive and negative terms. Choosing the correct test is an important first step before solving any infinite series problem. In the following section, my teammate will explain how these tests are applied step by step using practical example.
Good day everyone. Now I will present a real-life use of convergence series, which is drug concentration in the body. In medicine, after a patient takes medicine, the drug concentration in body will not remain the same forever. It will slowly decrease because of the body remove the drugs through metabolism and excretion. For this example, we assume that the drug concentration decrease by a fixed percentage every hour. Since the amount becomes smaller and smaller over time, this situation can form a convergence series. Next, I will show the problem scenario and explain how the series is formed. Now, let us look at the problem scenario and form the series. A patient takes medicine with an initial drug concentration of 100 mg per liter. After every hour, only 70% of the previous concentration remain in the body. So at the beginning, the concentration is 100. After 1 hour, the concentration become 100 times 0.7 is equal to 70. And after 2 hours, it becomes 100 times 0.7 squared equal to 49. And after 3 hours, it becomes 100 times 0.7 cube equal to 34.3. And the same patterns continue. So after 4 hours, the concentration becomes 24.01. Therefore, the concentration from the series, and this series will be tested using the ratio test in the next slide. Next, we use the ratio test to check whether the series is convergent. The general term is An equals to 100 times 0.7 power of n, where n start from 0. This means when n equal to 0, the concentration is 100, so it represents the initial concentration. The next term is An plus 1 equals to 100 times 0.7 power of n plus 1. So by applying the ratio test, we take the limit of An plus 1 over An. After substituting the values, the 100 can be cancelled and the 0.7 power of n also can be cancelled. Therefore, the final value of L is 0.7. Since 0.7 is less than 1, the series is convergent by the ratio test.
Okay, so my name is Cheng Yijin, and now I'll present about the case 2. So this case study presents real-life applications of a divergent series in computer science, known as the Cocoon collector problem. It is commonly used in cloud computing, database synchronizations, and also the software testings. In this system, encrypted data packets are transmitted randomly, and some packets may be received multiple times while others still missing. And this example, the cloud storage system contains 100 unique encrypted packets. During every transmissions, the server randomly sends one packet with equal probability, and our objective is to determine the expected number of transmissions required before all 100 packets has been successfully received. Okay, so the mathematical model is developed by calculating the expected number of transmission needed for obtain each new packet. And for the first packet, since no packet has been collected yet, so the probability of receiving a new packet is 1, requiring only one transmission on average. And after one packet has been collected, the probability of receiving a different packet becomes 99 over 100. So the expected number of transmissions becomes 1 divided by that probability, which equals to 100 over 99. And this process continues until the final missing packet, where the probability is only 1 over 100, requiring 100 transmissions on average. So by assuming all these expectations, we obtain that the formula is En equals to NH, where the H is the harmonic number. So the expected value is based on the harmonic series, and the harmonic series is formed by adding the reciprocals of positive integers. And here we calculate several partial sums. We observe that the value increase from 1 to approximately 5.1x7 when 100 terms are included, Although each additional terms becomes smaller, each term is still positive, causing the total sums to continue increasing. These are the characteristics of a divergent series because the partial sums never converge into a finite constant. So using the harmonic number for 100 terms, which is approximately 5.1874, we substitute into the expectation formula. The calculation gives an expected value of 518.74, which is approximately 519 transmissions. This means that although there are only 100 unique packets, the system requires an average over 500 transmissions because many packets are repeatedly received before obtaining the final missing ones. Since the harmonic series diverge, the expected number of transmissions continue to grow as the numbers of unique packets increase. Okay, so the results show that collecting the final few missing packets is much more difficult than collecting the first ones. This is because the probability of receiving a packet that has been not yet been collected becomes very small, leading to many duplicate transmissions. This mathematical model is widely applied in cloud synchronizations, distributed database, randomized algorithms, software testings, and also the network communication systems. And the engineer used this analysis to design a more efficient transmissions protocol and redundancies techniques. In conclusion, the Kopun collector problems demonstrates a practical applications of the harmonic series. For 100 unique packets, approximately 519 transmissions are required on average. These examples also illustrates an important properties of the harmonic series. Although its terms become smaller, the total sum continue to increase without approaching an finite limits.
Hi, I am Lee. Now I will explain the visual analysis part. In this part, the graphs are used to compare the behavior of two series. Case 1 is the drug's concentration decay models, represent the convergent geometric series, while the case 2 is the Coupon's collector problem, represent the divergent harmonic series. So the main focus is the partial sum. For a convergent series, the partial sum approach a stable limit. For a divergent series, the partial sum continues increasing without a fixed finite value. For case 1, the drug concentration follow the formula Cn equal to 100 times the 0.7 n, where only 70% remain after every hour. From the first graph, drug concentration against the time, the drug concentration decreased quickly at the beginning and gradually approached to zero. From the second graph, partial sum of drug concentration series against the time, the partial sum increased at first, but then become almost flat and approached to 333.33 milligrams per liter. So show that the partial sum approached a fixed finite value, therefore the series is convergent. For case 2, the graph shows the harmonic partial sum against the number of terms. It shows the partial sum continues to increase as the number of terms and increase, although the increase becomes slower. It does not become flat and does not approach a fixed limit. For the real-life interpretations, about 519 transmissions are required on average to collect all the hundreds unique packets. Therefore, the harmonic series is divergent. Overall, the graph shows the difference clearly. The convergent series approach a stable limit, while the divergence series continues increase without a fixed finite value. That's all for my part. I will pass to the next presenter.
Mm. Hi, I'm Yawisan, and I will make a conclusion for our project. This project demonstrates that infinite series are powerful tools for modeling real-world phenomena. Through the medicine and computer science case study, we highlight two distinct behaviors. The first one is convergence. The drug concentration model shows that process decaying by a constant ratio will settle at a finite limit, allowing for the prediction of stable long-term outcomes. And for the divergence, the coupon collector problem ensures that harmonic series grow without bond, even as individual terms are decreasing. The cumulative requirement for large-scale data synchronization remain unbounded. So in conclusion, mastering this mathematical theory is essential for analyzing system behavior and designing the efficient solution across various professional fields. And that's all for our team. Thank you.